to get into before the talk, but we want to thank Telerik for the t-shirts and the hat. If you haven't gotten one, just run over and grab one. They sent us a box of stuff. So thanks to Telerik. And thanks to Omni for sponsoring the pizza and the soda. Yeah. Jackie, did you want to say anything?
Yeah, I want to take a few minutes and talk to you about Omni Resources. We appreciate being able to sponsor tonight. For those of you that don't know Omni, we're an IT consulting company, have been in business for 30 years, an office in Madison, an office in Milwaukee, and an office in Appleton. And 2 lines of business. Probably the one that we're known the best for is just our IT consulting, where a client says, I need a Java developer, I need a program manager, or a network engineer. We have someone with those skills that we put into that position for the life of that. The second line of business that we have, we call our solutions group. It's an in-house development center, and we've got people that work for us full-time in our development center in all 3 of our offices as well. And so there a client will say that they need a web project done or software developed, mobile solutions, and so we'll do that in-house for them. So the solutions group, and the other thing that differentiates from us from other companies is that we're an employee-owned company, have been for 5 years. So everybody that comes to work for us becomes a employee owner and is earning stock in the company every year. So a little bit different slant. On our consulting side, we've gotten a little bit more old-fashioned. We want consultants to stay around. We don't want to hire you to come in for 6 months and that's it. You're out looking for your next gig or project and we're moving on. We want people that we can keep with us from project to project to project so that they can build their tenure, build the stock that they own. Patrick Sy was kind enough to come along with me tonight. He works in our solutions group, and he's going to tell you a little bit about what life is like in the solutions group. I left some brochures and some business cards over there. If your company needs any solutions, any development projects, needs consultants, get a hold of me. Our solutions group is almost always hiring. We're growing at a really good rate of speed. So Patrick's going to tell you a little bit about what he sees, what he does.
Hi, I'm Patrick Sy. Work for Omni Resources as an open source developer, mostly in the Java area. Brief history of my Omni story. Before Omni, I was with consulting right out of college. Went to state job when I came to Madison, so kind of 2 ends of the spectrum. Looking for something a little bit more, looking out there and found Omni. Solutions group was pretty cool. Consulting and yet work-life balance kind of thing put together. It was really good. Lots of opportunities for good technologies. Got hooked, got pulled in. The employee-owned thing was great too. Stock options, can't go wrong with that. So I got in. Now here I am, happy Omni employee. Things mean a little bit more now. I've seen some projects go by, really cool technologies. Met all these top-notch people. I don't know how Omni does it, but they've got people that really know their stuff and are nice, so you can learn stuff. There's educational opportunities still being developed in-house, lunch and learns and other things. And this, again, it comes back to the employee ownership thing. Stock options, great, but it kind of makes it more of a family rather than working for a company, you're working with the company, and whatever you do affects everyone else. So it's a great place to work. I like it. I have a happily ever after ending so far. Hope you can have one too. Thanks.
I also want to say thanks to Hani for recording all of these and taking the time to take all the content and put it on YouTube. You can check out all of the videos and upcoming events and our code of conduct, all that stuff, up on MadJavascript.com. We also have codes for front-end masters and O'Reilly books, so you can get 50% off O'Reilly books, which is awesome. We have some really good stuff there. Any other announcements?
company, Pinpoint Software, is looking for a senior JavaScript developer. It's going to be a full-time position doing a lot of stuff with Angular, JS, and Ionic. So if that sounds like something you'd be interested in, let me know.
Thanks. Any others? Okay, that's all I had. Report.
Okay. Hi, my name is Mikola. I am a graduate student at the university here. I also do some consulting work, just mostly part-time freelance stuff. On GitHub, my handle is also Mikola Lysenko. I write a lot of modules on NPM, so I think like now it's at something like 340 or something like that. And I am here today to talk about a project that I've worked on with a couple of my friends from the internet called Stack.gl. So, to get things started, I'll just open up this page and show you a couple of demos first, and then I'll go into the details. So this is maybe like backwards, right? But I figure I'll just blow your mind with this, right? And then the fact that I didn't finish the rest of the slides won't matter as much. So here, so I'll just show a couple of things. So in a nutshell, Stack.gl is basically a set of tools for building Webgl applications out of tiny modules, over NPM. So you can do things like data visualization, surface plots and stuff. It's been used in a couple of like industrial or enterprise level projects. So this is a project built by Gaëtan Rendau, and I'm sure I'm butchering his name, but he's based out of Paris, and so he wrote this like little system here using Stack.gl to do transitions in your browser. There's also some fun things. So here's like a little gadget that I whipped up where it's like a little thing. You basically take an animated GIF and then it renders it in 3D using like ray marching. Here's a couple of like other random bits. So this is sort of like a voxel Minecraft type thing, which basically like runs in your browser. You can use this to like look at other types of objects and stuff. So, sort of funny. So yeah. So these are the kinds of like little bits. It's also been featured on the Camp.js webpage. So if you look here, the background is all built in Stack.gl by Hugh S. Kennedy. A couple of other interesting. I'll go back here. Also, node source. So Hugh S. Kennedy is one of like the main people over there. So he's built the background for this bit here. So all like these interactions are all done using bits of Stack.gl. And there's like plenty more examples that I can kind of like pull out over here. So that's it. Oh, and then also I should mention Plotly, who I currently am doing some work for on the side. So they have like a web-based 3D plotting and data visualization thing. So you can think of this as something like a replacement for Excel. And they also support 3D plots in your browser. So you can do like a bunch of kind of fun stuff. So like these are, just like random plots people have made. So this is like a little Hilbert curve. And you can like select the different data points and stuff and see it in your browser. So yeah, that's, oops, didn't mean to close that one. So that's just some demos, a high-level, like 1,000-foot picture of kind of what this is all about or where this all ends up. But first, let me maybe start out by talking about WebGL. So I wasn't sure how much I should assume about this for the audience here, right? But I mean, I guess as just a quick poll, how many people here know roughly what WebGL is? So, okay, most people have heard of it. It's basically an API for drawing triangles. Like really, really fast and lots of triangles. Technically speaking, it's pretty much OpenGL ES2, just ripped out and then ported into JavaScript. So it's exactly the same API that you would use in like Java or Objective-C on Android or iOS for writing graphical applications. So it's just one-to-one, the exact same mobile, stable OpenGL API, just accessible from a browser. So the result is that you get pretty much the same performance that you would have for writing like an Android or iOS native app, and you're able to access like 100% of the hardware, except you can just run it in JavaScript and with no plugins and inside a browser. The support for it is pretty good these days. In fact, you can use it on pretty much everything. So as of IE 11, it's now available, on Internet Explorer, and the latest iOS and Androids now also support WebGL. So it's not a big deal. To go into like maybe a little bit more of the details here, with hopefully not going too far into this, right? OpenGL and any modern rendering library looks kind of similar. You have this sort of pipeline which is running, in parallel asynchronously from your computer. And what you do as a programmer using this API is you upload programs. So these would go in the these like little red boxes here. So these are programs that run on the GPU, and they're called shaders. And then you send commands to the GPU and upload data to it. And then these shaders basically take this data and turn it into vertices, which then get turned into polygons, then rasterized, and then colored using fragment shaders. And then finally, this all gets composited and pushed out to the screen. So how many people here know a little bit about shader programming or know much WebGL? So going like one level below WebGL, how many people have actually tried like using it or know about OpenGL or graphics programming at all? So so that's a much smaller group. So maybe this was not, maybe I didn't put enough detail in this one. That's okay. So, all right, so how many people here know what a shader is without looking at this slide, right? So maybe you've heard the word shader before. Okay, so shaders, they're just like tiny little programs which run on your GPU, right? And they get run millions and millions of times every frame, right? So for every pixel on the screen that you see when you're rendering something on the GPU, there's usually a tiny little program called a fragment shader, which is executing multiple times for each of those pixels that gets drawn. And you can write that program yourself in this fancy language called GLSL, and you can then push it out to the GPU. So there's basically two types of shaders that you have, fragment shaders and vertex shaders. So vertex shaders take data, so basically like just big streams of like vertex data, and then they can transform it or do some computation with it and compute vertex positions, which are then transformed and turned into triangles. And then those triangles are then rasterized and then turned into pixels, which are colored by a fragment shader. So the input to a vertex shader is basically the stream of data, which comes from vertex attributes, plus these uniforms, which are just broadcast out to every instance of a vertex. And the output are vertex positions and attributes, which are then interpolated and rendered in your fragment shader. And fragment shaders, they can also receive these uniform global values, and the output from a vertex shader. And then what they compute are colors at the end of the day. So that's a lot of stuff. It's maybe a bit much to take in and like learn it all at one shot, right? But there are resources that you can use to help learn this, right? Most notably at nodeschool.io, there's a bunch of free lessons that you can access here online. So if you go to this web page, maybe you've all seen it or not, I don't know. There's a ton of like these sort of self-directed lessons that cover all kinds of material. So the core lessons are basically JavaScript, Node, Git, and streams, right? And then from this you can then kind of build up and learn a variety of other skills, right? So for Node School, me and US Kennedy have put together a couple of like little self-directed learn at your own pace workshops that you can use to teach yourself WebGL, or if you go to one of these Node School workshops, so for example at NodeConf or Camp.js or other places we've done these, you can learn, in a more sort of directed environment, how to write GLSL code. So I'm just going to open this up very briefly and show you what it looks like. So basically, the way this works, right? So I'll just actually run it here. So if I just run npm start here, what it'll do is it'll basically create a directory full of some files that you can then edit using your favorite text editor. And then it'll just open up a little web page like this where you can take on any of the different lessons. So they start out pretty easy. So in the first lesson here, all you pretty much have to do is like just change a value from like 0 to 1 in order to make it work. So you basically can click this button here, then it shows you, like a description of the exercise. Then you can go into this folder, you get a file, which I guess I lied when I said I wasn't going to open up any code, right? But you basically have to just change this value. So 1-to-1, save it. And if you go here, it reloads, and now it's okay. And then you can check your solution, and if it's correct, then it says you pass. So they start out really easy. They get harder. You can learn how to do stuff with like vector arithmetic. So they cover all kinds of things. So and then they get up to like more advanced stuff. So you can like learn how to do things like lighting and other more sophisticated types of operations. So in each of these, you can actually compare like side by side what the lighting is supposed to look like versus what it is. And then it also even gets into like GPU programming. So you can learn how to do stuff like write cellular automata that run on the GPU. So, and by the way, like I should mention that you can like compare your solutions side by side, check out the code. You can also do like overlay or other kinds of stuff. But yeah, so that's Shader School. This teaches you GLSL. Yeah, question?
Why are they called shaders?
Yeah, so this is a kind of legacy name. They're actually just programs, right? But the concept of a shader was introduced by Pixar and RenderMan back way before GPUs were even a thing. And so what Pixar used shaders for was in their rendering system. They wanted to have some method for like artists to basically insert bits of programmable functionality, like change the shading on a surface, right? So they'd have like different kinds of like functions that you could write that would calculate colors or perform different sorts of subdivision operations. And so the original term shaders has to do with shading for the purposes of shading an object. So you can actually, in Shader School, if you go through this lesson, you can learn how to actually do things like non-photorealistic rendering or like cell shading. So assuming that I didn't, this is actually my local copy of it here, so it actually has a bug in it right now, so that's an unfortunate thing. But you can learn how to do things like flat shading or like point sprites or other types of stuff, right? So you can actually like implement the lighting components yourself. So that's Shader School. The dual to this, or the sort of other side of this whole equation, is Webgl Workshop. So Shader School teaches you GLSL, which is a programming language for writing shaders. Webgl Workshop teaches you how to use these shaders in Webgl in JavaScript. So once you know how to write shaders, then you can learn how to do more advanced stuff with WebGL. So that's what's covered in this lesson here. And I'll just go do that really quick and pop this up. So again, it's kind of the same story. And then you can basically go through and try learning some of like the different techniques here. So they start out like really easy. Basically like the level of like how do you clear the frame buffer, and then they move up to more advanced lessons like how to do stencil shadow mapping, right? So yeah, these are kind of, so here's like stencil shadow. So it shows you, the interface for this one is a little bit different. So here on the upper left corner you see what it's supposed to look like. You should have like a little bunny with shadows, and then here you just see the shadow volume getting rendered. And so it's up to you to basically set up the stencil operation so that when you render the shadow volume, it'll actually draw the correct shadow mapped object, or stencil shadowed object. So all of this stuff is explained if you work through the lessons and then do this stuff. And this is important, but it's not exactly part of Stack.gl, even though these are all written using Stack.gl. There are also more resources out there for learning WebGL. So there's WebGL Fundamentals, which is actually a really fantastic website. I'd highly recommend this one. And then there's also the official like WebGL specification, which is actually the same as the OpenGL ES2 specification for all practical purposes. And there's also a lot of other alternatives out there, right? So there are tools like 3JS, which is almost synonymous with WebGL these days, and things like Cesium, which are optimized like libraries for things like map rendering, and other scene graph-based libraries. But this is not what Stack.gl is about. Stack.gl is, instead of attempting to create some sort of monolithic super framework, right? So starting from some top-down view of how you would like 3D graphics to work, Stack.gl is more of an organic bottom-up approach. So it's basically a large ecosystem of many tiny reusable modules. So if I go here to the Stack.gl homepage, I can show you this huge list of packages. And so each of these things does one tiny specific function related to rendering. And so what you can do is you can compose these tiny functions together at various levels of abstraction to build more complicated components. So instead of being something like a pre-built, framework or 3D engine, it's more of a build your own framework from scratch type of approach, right? So you can build exactly the framework you need to solve exactly the problem you care about. It's built on top of NPM and Browserify. So all of these components can basically be installed from NPM. They're all semantically versioned. All of their dependencies are handled, in some, deterministic and reproducible way. And they're sort of grown organically, right? So anyone can kind of create a module and try it out, and they can all compete and evolve in some sort of competitive evolutionary environment. So ideas that are bad and not good will die, and ideas that are successful will propagate and become more useful and widely adopted within this ecosystem. And because they're all very small modules, they tend to solve well-defined problems, which allows them to make for smaller bundles. So instead of having to pull in some gigantic megabyte large, dependency for some 3D engine, you can pull in exactly the pieces that you need to solve exactly the problem you want. And because they are well-defined and they are smaller, they tend to have fewer bugs, they're simpler, and they end up being more optimized. So they can solve the same problem more efficiently than you would have to in some sort of like larger system. So in order to, say like implement texture arrays or some approximation of that in Three.js would require enormous contortions within the engine there. Or if you wanted to build, say, a voxel engine in Three.js, you would have to adapt to whatever vertex format Three.js expects, which could be extremely inefficient, and therefore you would be very limited in, say, your drawing distance for your terrain. So these types of problems can be solved by taking a more specialized approach, and using tiny modules is exactly what allows this to work. So let's kind of go through these different modules, starting from, say, the bottom up and then building up to like larger modules within the system. So we have at sort of this base level here a collection of modules that just manage the basic Webgl API. So all that these do is just take chunks of like the Webgl API and then encapsulate it in some simple low-level interface to reduce the amount of boilerplate that you have. So you can think of them as just like little shortcuts over common Webgl tasks. So for example here, we have GL shader, right? Which basically packages up this problem of creating and linking a shader, which is normally something that requires like hundreds of lines of code, if you want to do it yourself, right? Or maybe like, 100 lines to like create the shader and then set all your uniforms and bind them all together. You can now do this, automatically in one shot and just remove all of this boilerplate from your code. So this can handle things like, it can basically use like reflection to figure out like where uniforms have to go, and then it can bind the variables for there. And it has an API for setting up attributes and defining locations. So you don't have to like manually go through and do get uniform location and then set attribute location and all this other stuff, right? It can just take care of this for you. Similarly, like GLFBO is a sort of simpler API for creating a frame buffer object. So if we look here where the frame buffer is initialized, here, this is actually like the implementation of Conway's Game of Life, right? So if we click on this link here, this is a GPU Conway's Game of Life, right? The code for it is in this little snippet right here. So here we have two shaders, one that's basically taking care of updating the state of the game, and the other one which is responsible for rendering it. And so if you look in the initialize method over here, first we're creating the shaders, and then this is like all of the code that's required to create the frame buffers, and then this is all the code that's required to initialize the frame buffer, which is much less than regular like WebGL. So these things, you can accept them or not. They're in some sense optional, but they're just there to streamline the parts of OpenGL that are kind of crufty. So they're just tiny, very lightweight abstractions over parts of WebGL that are just there to reduce boilerplate and smooth out rough edges. They all follow a very similar interface where you have maybe a bind method to attach that resource to whatever attachment point, and then some update method which you would use to change the contents of that resource, and then a dispose method which you would use to release it when you're all done. So one thing in WebGL is that resources are not garbage collected, so you have to manually delete them right when you're done with them. So okay, so that's kind of like the first easiest thing that we can do. So okay, that's a start. It's not enough to really start doing much interesting, and so this is now where the next big piece of Stack.gl comes in. So there is the system GLSLify, which is essentially modules for GLSL. So in the same way that CommonJS allows you to write reusable modular JavaScript, GLSLify lets you take modules for GLSL functions and publish them to NPM using semantic versioning and the node module resolution algorithm and create stable, reusable shaders, right? So you can basically abstract out common functions within shaders, publish them, and share them with other people. And then anyone can take them and compose them together to build more advanced functions or build their own shaders, which are specific to their own engine. So instead of having to use some kind of janky templating system or some ad hoc graphical control flow thing, you can just write normal GLSL code, except you can just abstract out the commonly used pieces and share them. So here's an example of how this would look. So for example, this would be say some lighting calculation, which you might want to reuse across many different objects in your scene. So in this case, it's just a simple Lambertian light model where it's just taking the dot product of your light direction and surface normal clamping it, right? And so we might want to say reuse the same lighting calculation in many different scenarios. So in this case, this is just a one-line function, but sometimes these could become very, very complicated. So to give you an example of one of those, I can show you a more sophisticated lighting model. So this model here is the Cook-Torrance lighting model. It's maybe a little more complicated here. So this would be basically something that would allow you to have rim lighting on objects or kind of fancier reflections. And it uses as a submodule actually this other module, our method for calculating specular lighting, which is called the Beckman distribution. So this is actually a lighting model that is itself a composition of lighting models. And when you get into things like multi-layer, lighting models, those can themselves be compositions of more lighting models. And so in this sort of sense, it's natural to allow these things to just be ordinary code objects that can just exist, as modules on NPM and can just be installed there. So the way you'd use one of these things is you basically take whatever function you want to export in your module, you use this additional pragma, which is a preprocessor definition in GLSL, and then in the code that's consuming it, for example, your final fragment shader, you can just grab that one chunk of GLSL that you need, that particular function from that module, and it will just go, use your local, path and the same algorithm that Node uses for resolving dependencies through CommonJS, and it'll just grab that function and just stick it right in your shader there, and then compile it all together into one final block, right? So there's a ton of modules that exist for doing stuff in GLSLify. I mean, the easiest things are stuff like lighting models, which are a no-brainer to put inside there. But you can also put in more complicated functions. So, for example, in GLSL, there's no concept of noise, so you'd have to do a lot of work to do that. Also, reading floating point values out of GLSL can actually be kind of tough. So you can put that into a module and just reuse it. And then you can also use sort of helper functions. So for example, this is a module that handles this problem of dithering a function, right? So you have some image or something and you'd like to create a dither. So you can do this in GLSL just loading this function. So that would be an example of how that would work. So okay, so GLSLify is basically Browserify but for GLSL, right? Is one way you can think about it. It's just a preprocessor step that you can run your GLSL code for, and it'll just compile it and give you this sort of, modularized shader. Yeah, so any questions about that, right? Or no? Okay, so far, straightforward. So there's also functions for working with linear algebra, which are, again, sort of split into tinier modules. One convention that seems to be working pretty well so far is to use just arrays for vector types. So for many linear algebra libraries that you'll find out there on NPM or otherwise, it seems that there is this tendency to try to overuse object-oriented programming for creating things like vectors. This actually turns out to be extremely bad because you then have this peer dependency on that particular vector object. And if you change something in that, then it causes lots of breakage down the line. It also ends up being slower too, right? So in JavaScript, it's just faster to use arrays, and it's also easier to write robust code that has fewer mistakes. So if you want to do some component-wise operation, you can just use a loop, right? You don't have to like create, some cute vector.add or whatever. So the X, Y, Z type accessors are really not so good, and it turns out to be easier to just use an array, right? So a lot of these sort of more successful abstractions for working with vectors, it just turned out to be the simpler ones, so just ordinary stuff. And these techniques are mostly based on work by Brandon Jones through GLMatrix. The advantage to splitting them up into tinier pieces, though, is that if you want to only use just one function, then you can actually require just that one function from the module, and it will work. So, for example, here, instead of like, if say you just want to create a scale matrix, right? You wouldn't need to load the entire GLMatrix library to just use that one function. You can just require glmat4/scale, and then you just get that scale function. So it's in some sense smaller and easier to compose them together, right? And you end up with tinier code at the end of the day. And if one of these things changes, then the entire thing doesn't change, right? So you have smaller independently versioned pieces. For images and voxels, the current convention right now is to just use NDArray. So NDArray is another project that I worked on. This is basically a collection of tools for working with multi-dimensional arrays and sparse arrays in JavaScript. You can think of it as something kind of like a modular MATLAB. There's a bunch of different things you can do with it, and there's a huge list of modules that use this. So I won't go through the whole thing over here, but you can do stuff like image processing, MATLAB style, like matrix arithmetic and other stuff. There's a large library ecosystem. It's mostly useful for just working with assets and then also just like image transformations too. So those are the kind of easy things, but there's a lot more you can do with it. For meshes and geometry, one general approach that seems to have been somewhat successful is to just store geometry and not focus on trying to store commands and scene graph information. So the worst offenders in this category are Collada and VRML. So the problem with many of these asset formats is that they end up trying to create some reproducible, renderable 3D scene. And the issue is that everyone will do these things completely differently. So they really don't end up being reproducible or re-renderable. And so it's just a bunch of useless noise, having all this extra crap sitting around in your data structure. So for meshes, it's easier to just store a simplicial complex, or basically a flat indexed array of triangles or faces or whatever you like, and attributes. And this is probably the simplest and most robust low-level data structure for passing around geometry. It's basically to show you how this works, right? So here's a simple example of this. So this would be a tetrahedra encoded as a simplicial complex, where you would have basically the faces of the tetrahedra encoded as these three tuples of indices of vertices, and then the positions would just be stored in an array of triple arrays of vertex positions. And you could even flatten these out too, into a flat array, and then store them in, say, an NDArray in order to optimize it further. But these types of very simple data structures turn out to be more effective for storing geometry and processing it and working with it in WebGL than any of these more complicated, insane, over-engineered formats. So if you want to get your hands on some test data in Stack.gl, that's generally pretty easy. Again, they can all be obtained through NPM. So one nice thing, if you want to just grab a mesh and start working with it, is you can just do, say, npm install, bunny, and then you have a copy of the Stanford bunny right there. You can require that bunny, using, again, whatever common.js method you'd like, and you can just access, the properties of this bunny directly, right? So you just get the cells, positions, you have the faces and vertices, no sweat. And there's also other, data sets that are out there. There's also a variety of different file parsers that are available because, again, they're all just on NPM, so you can just look for, whatever format you like. So if I wanted to find, say, a PLY parser, I can just type in parse PLY, NPM install that. Now I have that one component. I don't have to go out there and do this other stuff. So there's just this huge list of different parsers and formats that you could take advantage of. So I think it's safe to say that with this type of approach, you can deal with literally any type of geometry that's out there, right? You can just grab whatever parser you want, read it in, and then work with it. Again, though, this again comes back, though, to the Collada and VRML nightmare, because those particular formats tend to be somewhat more annoying to work with because they have all this extra junk sitting around inside them. So usually all you want is just the geometry. You know, you don't want all of the extra scene stuff. But you can still get that data out of there. It just becomes more work to deal with that other stuff once you have it there. And for extra tools, so there's a variety of tools that you can also use, you know, for just generating geometry from scratch. So for example, if you want to, like say, build like a polytope or something. So what if you want like an icosahedra and just type I here and get that, or, you know, C, or generate any old like crazy random thing. So like this module here, what it does is it basically takes a string. I'll show you what the string looks like. Right, so this string here is basically a seed polytope plus like a list of operations that you can apply to it. And what it'll do is it'll basically apply these subdivisions to the operation in order to build some more complicated polytope. So instead of having like just like a list of like, you know, canned data types or whatever, you can generate your own kind of crazy looking, you know, 3D polytope and then render that if you like. So that's one simple example of it. There are other modules here too. So we have you know, a variety of different approaches for rendering text now. So for example, this module, what it does is it takes a string of any sort and you give it some parameters, and then it'll just you know, trace a curve. So you'll get like a polygon out of the text, or you can render, you know, a closed set of loops or a triangulation. And then with this triangulation, you can then do your, you know, standard 3D like Webgl processing, right? So if you want to work with like text, which Webgl doesn't come with anything built into, I mean, it only draws triangles, you need to have some way to take your string and then turn it into text. There are also tools that we have for working with isosurfaces, so you can do things like, you know, f of x, y, z equals 0 type solutions, or sort of like surface contouring techniques, so stuff like marching cubes or dual contouring stuff. Convex hull, you know, in any dimension, right? So you want to do like a 4D convex hull, you can do that too. And then like surface voxelization stuff. So, and there's lots more stuff, right? And again, for each of these things, they're not all like bundled into one giant like mess, right? They're all separate programs, which can be installed selectively for solving that specific function. And if you want something that solves that function, you just install it and you use it. So there's an enormous amount of stuff that you can do with geometry in Stack.gl. There's also a lot of tools for data visualization out there now. So we have, I'll just kind of throw this thing up here really quick. So you can do stuff like surface plots, or, you know, contour plots, or you know, however you want to do it. So like scatter plots for point sets. I'll just take a surface plot here. So like I think I showed this demo earlier, but this is like a surface plot, and it can actually do like these sort of contour highlights too. You know, and then like this is also all using like different chunks of like features here. So like the surface material is actually constructed using that Cook-Taran sliding model, and then there's you know, other. So the background here is actually that GLAxis module that was just installed and used for this purpose. These contour lines are rendered using those surface nets. So it's all just, you know, these tiny little pieces all put together to build, you know, some larger, more complicated thing. So, yeah, and then there's also line plots too, right? As if, you know, there weren't enough plot types here. So these plots were, in a sense, sort of funded or developed for Plotly. So these are actually in use in production on Plotly /plot, right? So if you go onto their webpage, you can see all this stuff live. So, right. There's also a variety of tools for managing all of this. So one really useful program is Beefy. So what Beefy does is it's a local Browserify development environment. And if you haven't used this before and you use Browserify, you should be using this program. So it's basically like a live reloadable Browserify server. So whenever you make any change to any of your code, or, you know, you install a new module or whatever, it'll just reload your page, and so you don't have this kind of confusion between when, you know, something gets updated, you know, and like when you need to refresh or whatever. And it also handles all the source maps and other debugging information. It integrates with GLSLify and all these other things. So it's really like very nice for building this stuff. And then also for working with GLSL. So GLSLify, like Browserify, supports a concept of a transform. So you can do things like apply an optimization to your shader, or add syntactic extensions to GLSL, or create your own compiled to GLSLify language, like CoffeeScript.glsl if you felt inclined. And like one place where this turns out to be very useful is for reducing your shader size. So what GLSLify Optimize will do is it'll take your GLSL that's produced from GLSLify, and it just runs it through basically a minification filter in place, and then sticks that right into your code inline, right? So you don't have to deal with maybe like a bunch of like bloated stuff sitting around in your GLSL file. And then there's also tools for like live reload of GLSL, so you can like edit a shader, then watch your shader change while your program's still running, that sort of stuff. So in the future, though, I mean, these things can always get better. Like, there's definitely a need to, build more tools for doing debugging and testing. There's also, I think, a kind of unsolved challenge, but I think we have some ideas for how to do it, and I think it's just a matter of finding the time to get there to work for multi-pass lighting. I mean, there's sort of like easy ways to do this, right? But the question is, how can we do it as efficiently as possible? And then also just building more features and like building up this whole system so that it can do even more, right? Which is, something that we can, definitely handle because it's, has this sort of solid, simple foundation, and it's very easy to just kind of extend it and add additional pieces into it. So we can always like take more stuff and incorporate it into this ecosystem of different tiny pieces. Some contributors here, so the main people here, I guess there's QS Kennedy, who is probably doing a lot of work right now. Chris Dickinson did much of the early work on GLSLify, and he's been very active. And then also Matt Deslauriers, who I'm also probably butchering his name, is doing a lot of work these days with building sort of like new geometry tools and then also new shader effects. If you want to get involved, you can hop on Stack.gl on Freenode, or on Twitter or GitHub at Stack.gl. There's also, I think the main place where you'd probably want to get in touch with people is through IRC though. So I would probably recommend this avenue first. And then there's there's the website too. So right here, yeah. And again, also built using the same collection of tiny modules. So. Yeah, that's kind of a high-level 1,000-foot view of this whole thing. Any questions about this so far, or wherever? So, yeah, sure.
How do you handle interactivity?
Yeah, that's just done by hooking stuff into the DOM, right? You just basically hook a key event. You can use a module to do that, or you can just do it yourself. So there's a variety of different tools out there. So one would be you can use like vkey or onEvent. I mean, there's like hundreds of different things on NPM that can just do the interactivity. So if you want that interactivity, you just use whatever input handling library you like and use that.
But don't all of those objects inside of Webgl, isn't that in its own container? That is still those each have elements in the DOM.
No.
So if you were to click on something inside of the WebGL container,
it's very much like a canvas object, right?
Yeah.
So from the perspective of the browser, WebGL is just like a dumb array of pixels, right? Like it doesn't have any like sort of event bubbling or whatever. So if you want to do like event interactivity, what you get to work with are like key presses and mouse clicks, right? You don't get like event propagation.
So how would you know you put down the bunny, you tapped on the bunny's ears, for example?
So there's a couple of different ways to do this, right? So if you want to do that, that's a problem called picking. I mean, if you saw, right, like you can do it, right? The way that this is done so one way to do it is you can basically render 2 copies of the frame buffer, right? So you basically like have like a displayed buffer, and you have an off-screen buffer. And then in the off-screen buffer, what you do is you just render your entire scene using, say, like a different color for each pixel that corresponds to the object that you're selecting. And then what you do is you just read that pixel out of that buffer, and then it can tell you what you clicked on. And so that's actually automated by this module GLSelect. So what you do is if you just follow the sort of protocol of how you color your pixels, which you can again sort of streamline using another module from GLSLify, then you just color your pixels appropriately, and then you can just read them out of this buffer here, and it gives you the coordinates of where you picked and all the other data. So this one just handles like the reading the pixels and then setting up that extra frame buffer for you. So the short answer is with a module how you do that.
So you can build a mini CAD system on top of that based on what you just said?
Sure. Yeah, you could. Right. Yeah.
Are there any problems overlaying HTML or SVG on top of WebGL? I'm looking at Canvas.
Yeah, you can do that, right? And there are actually tricks that you can use to like render like HTML elements behind, or like to actually embed an element in 3D. It's a little bit weird, right? But what you do is you basically apply a CSS 3D transformation to the element, and then put it behind the WebGL context, and then you just alpha blit out like a region, right? And then you can render it in the 3D scene, right?
What if you just want to lay it on top, like you have a label or something?
Yeah, no problem. I mean, it's just, from the perspective of the browser, it's basically like a canvas element. So you can put an SVG thing on top of a canvas element or a text thing. No, it's exactly the same as like a canvas element,
So
right?
is that like CamJS or the...
Exactly, yeah, that's exactly how those work, right? That's how those websites are built. So if you look at like, Camp.js, in the background here, right, this is basically like there's even like a YouTube video here, right, that you can watch, which is basically overlaid on top of the, WebGL context, which is running in the background. Right, so it's just like a normal canvas element, right? There's nothing fancy or special about it. Yeah.
Can you talk about Android browser support?
I don't-
How does it go back?
Well, we can go to the authoritative source, caniuse.com. Chrome for Android 39 and the latest Android browser. All right, so I guess this was not actually officially deployed yet, but there's an asterisk there. So apparently in Android browser 37 it should do that, and the Chrome for Android it'll work. So yeah, iOS though is good. I know because I have one, so it's
Mobile Chrome for Android just recently got WebGL.
yeah. The short answer is that within a year, for sure, right? Probably less time. Everywhere will have WebGL, so it's just going to be part of the web at this point. Yeah.
So how do you see it being used in the future?
All kinds of stuff. I think data visualization. I think also for like offloading certain computations, so you could use it for things like computer vision tasks. Sort of like smart applications that combine with, say, WebRTC to create more interactive stuff. A lot of advertisements, I think, will probably want to do stuff in 3D because it'll just like look better. You could also start offloading like some image processing or video processing to WebGL too. So you could imagine like maybe completely browser-based video codecs. All kinds of stuff, right? So I think pretty much once WebGL becomes a standard, it'll basically allow you to get every like the same level of performance you would have in a native application just in a browser. And then also games, right? Yeah, that's the other big one too. Right, video games. Yeah.
Could you talk more about the Chronos group?
Yeah, so the Chronos group is basically this independent review board that oversees the WebGL specification and actually OpenGL ES, which is what WebGL is based on. It's just this independent industry consortium. It's basically just like a bunch of different people from like CAD vendors and like video card companies and whatever that all kind of agree on what the next OpenGL spec is going to be. So it's sort of like the W3C just for OpenGL.
Is there anybody working on a similar Stack.gl that would sit on top of WebCL?
Well, first of all, WebCL would have to be a thing, right? That's the real problem. As far as I know, there isn't actually a single working implementation of WebCL at this stage. Also, like longer term, I think that there are some issues with OpenCL in general because it's kind of a race, right? Because eventually, like, compute shaders will become standard, and I think it'll become kind of irrelevant, right? Which is kind of sad, but that's just what's going to happen, because compute shaders, you can basically do everything that you're already doing with OpenCL, except without having to like create a brand new API. And then there's the additional problem that a lot of OpenCL implementations aren't actually running on the GPU. Like, they're just multi-threaded, right? So like on Apple, or like a lot of like, Apple devices, like you don't actually get GPU acceleration with OpenCL.
Well, everything they ship supports it on the GPU, but
Yeah, but it doesn't always run on the GPU. Or maybe it does. I don't know. All right, so last time I tried it, I was not able to actually get the hardware acceleration to work. So maybe this was my own mistake in using it. But I don't know. I was not super impressed with my last experiment with OpenCL. But maybe WebCL will solve it, right? If it becomes a thing. But I don't know. I'm not privy to the inner details of how that works, so I wouldn't. I'm not going to speculate any further on it. I don't know. Maybe. Yeah.
So when you have a standard way of creating these modules, and they're so, like, the idea is to make them extremely small, right?
Right.
How are you creating a community around those many small modules so that there's a lot of people that know about the different implementations?
Yeah, well, that's why we have like a Stack.gl like organization on GitHub. So many of these modules are owned communally. So we have multiple contributors that own each of these modules, and there's this larger community here for people to come in and discover them and then get up to speed. And also, if you just go on IRC, you can talk to people. So in this sense, it's not any different than any other like large open source project. Like, who on earth, besides maybe a few people, know every piece of Three.js, right? I mean, it's like you go in there, you talk to people, you learn about parts of it, and then you discover, all the different pieces. In this sense, it's just that rather than being all bundled into like one single software object, they're still, linked by a common community, but they're all just in one common directory of software components. It's just we don't make any special distinction about them. They're just software components. Some things that do help with discovery, though, is we've been using this GL prefix on each of them on NPM, so that if you see that, then you know it's part of Stack.gl. And then also for GLSL components, they usually have a GLSL-prefix, right? So they're all, like if you see a module with a GLSL in front of it, then you know this module is actually written in GLSL. Or you can at least make a reasonable guess that if you click on it, it's going to be a GLSL module. So, I don't know, does that answer the question?
So by stars and installations.
No. It's by talking to people. That's how you learn about them, right? So you basically go to, IRC, right? Or you go to the web page. So. Yeah.
Does this exist for C and Java?
Unfortunately, no. The problem with C and Java is that they don't have adequate package management systems that would make something like this possible. So really, this only works because of NPM at the end of the day. Without a system like NPM, there'd just be no way to like manage all of the tiny little pieces. I think it would be nice to have something like this for C. I would certainly love to see it, but it's just I don't see any way to make it work with C's current, software dependency management system. And similar to Java, right? Like one problem, that is solved using a system like NPM is that you can actually have different versions of a module, right, installed at the same time. And in that case, NPM just installs 2 copies of it, and then nothing breaks. It's okay, right? But in Java, because all modules are loaded into the same global namespace, it wouldn't really work, right? Similarly, for C, everything is actually just like even sitting in the same space of symbols and like individual variables, so that also wouldn't work. Right, so I think it could be possible. You just have to build some tool for C that lets you write modular code in the first place. But I think in theory it could be done. Someone just has to build a proper C package manager.
There's a similar environment for C# that does have an instance, so in theory you can use it in C#.
Maybe, yeah.
But clearly the lion's share of interest people are
Yeah.
in the JavaScript world.
Well, and there's also an opportunity to do it over again in JavaScript, right? So you can try out some new ideas and see if they work, so that's actually viable to do it, and it makes sense to do it in JavaScript, so it's kind of a nice thing.
How do you compare it to your competitors, in your opinion?
I think that in some sense, they may not be even direct competitors, because I think if you really look at what Tree.js really does well, and I think like where its sort of core competency is, it's really like got the market down on drawing like a little spinning widget, right, in 3D. And actually, I think for like 99% of what people want to do in 3D, that may actually be sufficient. And with Stack.gl, the goal is not to create like a little 3D spinning widgets, but to create like more complicated interactive things, right? You can actually like select stuff and move them around, or do some non-trivial computation inside them. So for those, I think that there isn't any other system that's really going towards those types of higher level problems. They're all very focused on, how do we get, to the point where we can just draw a thing and put like some lighting and texturing and shadows on it and, just make it look pretty, right? They don't want to go, the next step further to actually start building larger, more serious systems. So I don't think there are actually a lot of things that are actually really trying to take that on yet. Yeah.
Can you speak a little bit about benchmarking and performance of, say, the WebGL versus OpenGL implementation in C or something like that? How much more overhead is there with the JavaScript?
I don't know of a good like apples to apples comparison, so I've never actually tried to set one up.
It seemed like only getting the geometry onto the GPU should make any difference there at all.
Exactly. Right.
The shaders are identical. They should
Right.
be a one-to-one comparison.
Yeah, I mean, if you're doing it right, I mean, once you have your geometry on the GPU, you're probably not going to see much difference, right? Now that said, there's probably more overhead in WebGL in terms of latency, right? I would bet that the throughput is probably similar, but the latency will be higher because you have extra compositing stuff that you have to do within the browser, right? So I would suspect that there's probably like a longer like delay from when you push a button to when you'll be able to see the effect on screen. But I think that if you're just looking at like raw frames per second, there's probably not much difference. That's my feeling, though. I don't know, right? Again, but for reasons similar to what you say. Yeah.
Do you know if anybody's using this as maybe an opportunity to get around the DOM entirely and put a UI framework on top of the GPU?
Yeah, they're I forget the name of it, but I've seen some people who tried some similarly insane things, right? So I know there's at least one or two people that are trying to do it. I don't know of anyone who's actually like turned it into something completely serious yet, but you could do it probably, I would say, right? You could, just blow up the whole DOM, and like build everything in WebGL, and probably would be faster, right?
It would have to be faster.
Yeah.
I think. Be a lot of work though.
Probably. Yeah.
On the font rendering side, it's pretty impressive the things you can do, building meshes and
Yeah.
lines and different things like that. I've seen another approach that builds a texture that's a distance field.
Exactly. Yeah, we have a module that does that. So
Oh, cool.
yeah, yeah. There's a module. Matt Dessel wrote that one. So right. I forget the right. This one, GL Sprite Text. Right. So this is a assigned distance field based text rendering engine that Matt wrote. There is a slight drawback to the text rendering using this technique, though, because it's sort of like limited in the fonts that it can do. So the way the vectorized text module works is that it actually, it's kind of insane, right? But it basically uses the Canvas 2D API to render the text string using, just like whatever fonts you have installed on your system. And then it traces the curve from that, like, image, simplifies the curve, right? And then triangulates it. All of this would be too much to do for like just this one simple thing, but they're all modules. So you can just grab a module that does each of these like little pieces, snap them all together. This only took me like, once I had all the pieces there, maybe an hour to write, and it works. Don't have to change anything, it's fine. So, these tiny like reusable things let you write really complicated and maybe kind of crazy like systems very quickly and very efficiently. So, but it takes a while to get going because you have to build up like a lot of basic infrastructure first. But it's starting to get to the point where it's really like beginning to take off now.
Efficiency is never a problem?
It's actually generally more efficient to do it this way than you would get it using one of these other like more frameworky type techniques.
If you could reach in and get the original curves, though, you could.
Yeah, that would be better, but you can't do that. Right, because the browser doesn't have any API for exposing that. I looked, I didn't see anything. Okay, I guess it's now after 7, so it doesn't look like there's any more questions. So I'll basically say thanks for having me out, and
Thank you. That was very good.
That was amazing.
yeah.